Hello, I would like to present proofs of the four kinematics equations we typically use in AP Physics, in physics, when we're first learning about kinematics, the study of motion. Um, so our premise for this is going to be we have a car or something, it could be anything, and it's initially moving with some initial velocity VO, and it accelerates in the same direction it's moving. So that's going to result in the velocity increasing in magnitude or going faster. It's going to take a certain distance, and there's going to be a certain amount of time associated with that change in speed and that acceleration. Now, a major assumption of this is that we're assuming that the acceleration is constant for this. It's a constant magnitude over that. It's not changing over time. So our variables we're going to be working with are change in position, time, initial velocity, and final velocity and acceleration. And once again, acceleration must be constant for these equations, these relationships be true. Okay, so I'm going to come up with these equations in this sequence, 1, 2, 3, 4. And these are our equations we have that we typically use. The first one ignores displacement. I should maybe put a little delta x right there. It ignores displacement. And I call that one little cutie because there's not a whole lot to it. By the way, these nicknames are not standards in physics. These are like just what I call them. So please do not refer to them on a national exam or anything. The second one I'm going to come up with is called the mean machine. It's based upon the average of those two velocities that our little car will reach here. It ignores acceleration. So if you don't happen to have acceleration, you can ignore that and still be able to solve for something in this equation. The third equation I'll derive is Big Nasty. It's just got a lot of stuff going on here. It's got fractions and squares and different stuff, so I call it Big Nasty. And this ignores final velocity, so if you don't know that, you can ignore it and still use this equation. And the fourth equation is SpongeBob SquarePants. It's got squares all in place. And this ignores time. You don't need to know about time to utilize this equation. Okay, so I'm going to start this one. And maybe I'll do it right here. Let's do it in purple, so it's really exciting. So we're going to come up with equation number 1 here. So what that looks like is V equals VO plus AT. And you should recognize this every year in math class when you've been learning about y equals mx plus b. Well, here's your vertical axis intercept, and here's your slope stuff right here. So this is just of the form y equals mx plus b, and so we're going to say, hey, here's going to be my VO, or my vertical axis intercept, and I'm going to be right there, and then some amount of time is going to pass. So, oh, by the way, this is a velocity time graph, and we're going to use that to kickstart all this stuff off. So we're going to start at time 0 at some initial velocity v0, and then sometime later, let's call this time t, we're going to be right here, which is going to be at some final velocity v. And so our rise over run is going to be our acceleration on this graph, and that's just how we get to this guy here. It's just the classic form of a slope-intercept. So that one's pretty easy. Okay, our next one. So we're going to go ahead and check this off. Okay, our next one. We want to figure out this mean machine equation, the one that ignores acceleration. Okay, so we're going to do some fancy action here. Let's see here. I'll erase this acceleration real quick. All right, so Between these two velocities here, our final velocity and our starting velocity, there's probably some average. It's going to be halfway average velocity, and the symbol for average velocity is V with a bar over it. You don't really need to have that memorized or anything. I'm just going to use the nomenclature here. It's not particularly important. Okay, and that's going to be exactly halfway between there. So let's maybe do this one. We're going to come up with equation number 2. And we're going to start out with, well, average velocity is just you add together two velocities, right? We're going to add together our two velocities for our situation here. And that's going to give us our average velocity. Okay, so that's going to be right there. Okay. But by the way, maybe I'm jumping ahead of things, but this is a constant slope, and we know for a velocity time graph that the slope of that is the acceleration. So this matches our thing here that it must be constant velocity by the shape of this graph. Anyways, so we have an equation for the average that you've probably learned about in math class before, and we know from our physics facts also that the area underneath a velocity time graph is going to be area of a VT graph is change in position. Okay, so let's figure out what the area would be for maybe, well, what if we did, oops, let's see here. What if we, instead of changing speed, what if we just did this average velocity the whole time? Well, we would go a certain amount of distance at a constant speed. We'd be maintaining this speed, and that would result in an area on this graph, which is the displacement. And this is your delta x in here. And it's interesting that the displacement of this graph is actually going to be the same as the displacement for this graph. That little trapezoid in here. You'll notice that the amount of area that this one is missing, that this trapezoid is missing over on this section of the graph, is going to be the same amount of area that it has extra over here. So actually, this trapezoid right here and this rectangle right here both have the same areas. So let's make a statement about that. We can say, hey, oh, I've got my transparency on here. Let me fix that real quick. We can say, hey, the area of this graph, or the amount of distance you cover during this time frame that you're accelerating, we can figure out by saying, well, that's just the average velocity times the amount of time, right? It's just this velocity maintained over that time period is going to be the same as increasing speed at a constant rate. You're going to travel the same amount. And so we know, though, that we have an equation for average velocity. It's V plus VO divided by 2 times T. And you can see it right there, isn't it? It's right there. That's our equation. So we've got equation number 2 done. Just to recap of that, was a little bit choppy, but we know that on the two velocities that our car starts at and ends at during this displacement are V and VO. We know the average is going to be halfway between there. Okay, we have an equation for average of anything. So average velocity equation is this. Okay. Also, through our physics knowledge, we know the area of a velocity time graph is displacement. And we know that this area of this green rectangle is going to have the same amount of area as this trapezoid. Okay. And so we use our idea about displacement is the area underneath the graph. So the area underneath this green graph is just the average velocity times time. Well, we know we can substitute in this average velocity equation, and we get this, which looks like the equation for a trapezoid, which sounds just great to me. That's what we're actually trying to find. Okay, next piece. Now, our use of this graph is kind of over. At this point, I'm just going to substitute these two equations together a few times and make these other equations pop out. All right, so let's try that out. Our next little phase we're going to do here is we're going to pick blue here. And we're going to go for equation number 3. Okay, so equation number 3, we take equations 1 and 2 and we combine them to make this guy happen, which is going to substitute out final velocity and leave us with this. Okay, so let's go for it here. We're going to start with our mean machine equation here. So we're going to start out with this. 1/2 v plus VO t. And we're going to say, hey, final velocity is actually this. We can, instead of v, we could write this stuff in its place. So we're going to write that one more time. Delta x is equal to 1/2. But we're not going to write final velocity. We're going to write this stuff. So I'm going to write VO plus AT in its place. And then we can write the rest of this stuff. Plus VO, all that times T. Now we got to do a little math review here. We can distribute this half and this T to all the stuff inside these curvy brackets here. So let's go ahead and do that. Be an excellent math review for us today. 1/2 times VO is 1/2 VO. But we also got to multiply that times T too, so we'll multiply times T. Okay, let's go to the next term. So this one's done. Let's go to this term, the AT term inside here. So we're going to multiply that times a 1/2. We're going to have an A. We're going to have a T, but it's going to get multiplied by a second T for T squared. Oh my gosh, we can see it starting to happen already. Okay, we're done with these first two terms. This last one, that's going to be a 1/2 and a T times that. So we're going to have 1/2 VOT. Cool. Well, we see that we have two halves of a VOT here. 2 halves is a whole. So let's rewrite this and simplify a little bit. Delta x is going to be equal to a whole VOT because we're adding 2 halves together. And then we have this little bit left over, and that's our big nasty equation, equation number 3 up here. Okay, and let's do our 4th equation. What color should I do? Okay, we're going to get the 4th equation to happen right here. How are we going to get that? Well, we're going to take equations 1 and 2 again. We're going to substitute them together. Okay, so equation 1 looks like this. V equals VO plus AT. Okay, but we can rewrite this and we can solve for T, so it's going to be V minus VO divided by A equals T. And in equation number 2, the mean machine, we can substitute this in. So let's write equation number 2. It's delta x equals 1/2 V plus VO T. Well, we're going to go ahead and take this stuff and boop, put it right in there. So let's write that again. Delta x equals 1/2 V plus VO, and we are almost done. This will happen really quick, and we will have it finished. Thank you for your patience. It's much appreciated. We got this little guy here. We're substituting in for T, right? Instead of T, we're writing what T is equal to. Okay, and with a little bit of squinting and some math facts, we can say, hey, I can move this half and this A over to the left-hand side, and that'd be 2A delta X. I'll let you ponder that for a second. I multiplied both sides by a 2, and I multiplied both sides by an A. Cancel that stuff over here, puts it over on the left-hand side. Okay, and on the left-hand side, you know, I was not a great math student at this, but now I remember. This is like the difference of squares. And if you were to do the, multiply these two things through these two things, you would find out that you'd have v squared minus VO squared over here. And that's all equal to 2A delta X. And we could do one last round. We could rearrange this so it says V squared is equal to VO squared plus 2A delta X. And there we go. There's number 4. And so we have derived these 4 equations here. A real quick recap. The first equation is just y equals mx plus b form for a straight line on a graph. Our intercept is the VO. Our slope is acceleration. This rise and run on a velocity graph, we know that fact from physics class, is the slope of the velocity time graph is acceleration. And so that happens pretty quickly. The second equation, the mean machine, is derived from our ideas about what it means to be an average velocity, or an average. Between this starting velocity and this final velocity, there's some average velocity between here. We call that V hat, or sorry, V bar. And here's the equation for an average. Okay, but by our physics knowledge, we know that the area of a VT graph is displacement. And if we squint and look at this very carefully, this trapezoid area here in purple and this rectangle area formed by our average velocity are actually the same areas. And so we can say, hey, our change in position during this time frame that this thing is accelerating, we can just get that change in position by taking the average velocity times time. We substitute in our equation for average, and we can get an equation for the area of this trapezoid, which looks great. Equation 3. After this point, it's just simply math. We just combine equations 1 and 2 together to substitute out. We substitute out final velocity. No final velocity, and we get big nasty. Once again, we just do some math again. We combine equations 1 and 2 in a way that it gets rid of time, and we get an equation that times SpongeBob SquarePants. Thank you for listening. I hope that gives you a little bit of insight of where these equations came from. It's not magic. It's just some physics and some math. You don't have to have these memorized, but if you're curious, here's where they come from, and understanding this might give you a little bit of extra insight how these are used and where they came from. Thank you for your attention. Bye-bye.